Okay, good morning everyone, and welcome to the first press briefing of the day at this 219th American Astronomical Society meeting.
All right, good morning. I'm Will Dawson. I'm a graduate student at the University of California, Davis. And let me just kick things off with a question. What is dark matter? What is this mysterious particle which is working so hard to hold our universe together, and at this very instant is effortlessly coursing through each one of us? And even as Steven Weinberg said last night in his talk, doesn't hold a place in the standard model. I wish I had an answer for you today. I can't do that, but I can give a clue. So today, our team, which interestingly enough includes our very own Jack Hughes here, is announcing the discovery of a galaxy cluster merger, which we are using to constrain the properties of dark matter. This merger is about 2 to 5 times further progressed than any merger observed to date, which is part of the reason why we've affectionately termed this the Musket Ball Cluster, because it's similar to the bullet cluster, yet it's older and slower. All right, I can't take credit for that. That's from our collaborator, Dan Maroney. But so today I'll discuss how we found this cluster, how we're using it to constrain the properties of dark matter, and why we believe that its older age is particularly significant going forward. This is the cluster, the Musket Ball Cluster, but before I get into the details of the image, a little background information will be helpful. So galaxy clusters are the largest stable structures in the entire universe. They themselves are like little universes, and that they contain the same matter proportion as the entire universe, being made up of about 86% dark matter, about 12% hot gas. And when I say hot gas, I mean about 1,000 times the surface temperature of the sun. And only 2% of their mass is actually contained in the galaxies. Now, what you can see in this image is a Hubble Space Telescope picture of the cluster, showing 2 concentrations of galaxies, one in the north and one in the south. Overplotted on this image is the weak lensing mass map, shown in blue. Then in red, we've plotted the Chandra Space Telescope gas map, showing you where that hot gas is located within the cluster. And as you can see, the different components are nicely spread out. That's one of the reasons why these merging clusters are so important astrophysically. They provide us dissections of the cosmos that are otherwise impossible. Making this image was not easy. We used 6 different telescopes. I won't go through all of them. I'll put the slides up on my website, which I'll give a link to later. But some of these were used to measure the total mass of the cluster, including dark matter. Some were used to measure the locations of the galaxies, and others, including Chandra and the Sun SDA, were used to map the gas. One interesting note is that this was the first time that one of these merging systems was completely discovered from the ground. Now let me go through a little simple movie of how we think that the system arrived to its observed state. So what I'm going to show on the right is a simplified movie, not nearly as fancy as Jack's pictures, but blue represents dark matter, red is the gas, dark matter plus gas is shown in purple, and then the galaxies are the little black dots. So first of all, we believe that the north cluster began in the south, and the south cluster began in the north. Then through gravitational attraction, because of their mass, they began accelerating towards one another. Eventually they collided, and now this is the point in the movie where the plot really begins to thicken. The galaxies actually pass right through one another, and this isn't any new physics. It's just that the space between the galaxies are so far, it's so great, that the likelihood of any 2 galaxies colliding is very unlikely, so their momentum carries them right on through. Now the gas, on the other hand, is much more evenly distributed in these clusters, and so a collision between 2 gas particles is much more likely. And so you actually find that the gas gets stuck in the middle. The interesting thing, though, is whenever we measure the total mass using weak lensing, we find that the bulk of the mass is located with the galaxies and not with the gas. And if you'll recall from earlier, the galaxies are 1/7 the total mass of the gas. So this means that there must be some other massive component located with those galaxies. We believe this to be dark matter. Now, by comparing and contrasting the behavior of this dark matter with that of the galaxies and gas, we can actually infer that the dark matter must be collisionless, like the galaxies, and unlike that of the gas. We're able to become quantitative in our measurement, and we actually find that the dark matter must have a cross-section approximately less than or equal to that of a neutrino. I should state, though, that this is not the first time that this measurement has been made. It was first made with the bullet cluster, and using computer simulations, Randall et al. Have actually found a tighter constraint. What makes this particular cluster significant, though, this finding, is that it's 2 to 5 times further progressed than similar systems observed to date, which is what I'm showing in the plot on the right. So the y-axis represents the time since collision. That's the time it took from them to collide to reach their observed state, and that's measured in billions of years. And then the x-axis is the collision velocity in kilometers per second. Now, the red and blue curves just tell you where we think the Musket Ball Cluster resides in this phase space. And as you can see, by comparing with the black dots, which are the other mergers observed to date, or some of them, they all reside around 0.2 billion years after collision, whereas the Musket Ball, we're seeing at it around 0.6 to 0.7 billion years after the merger. Why is this significant, though? Well, first of all, in the most general terms that I could think of, it's important to realize that every great advance in our understanding of the physical universe has been the direct result of understanding how things change with time. So we're really getting a later snapshot of this. I mean, the same reason is why Jack and Michele's observations are so important at high redshift. To be more specific, though, merging clusters are incredibly important astrophysical probes. In addition to constraining dark matter, like I mentioned, these are the most energetic events in the entire universe. They're a potential source of these extreme cosmic rays that are traveling very near the speed of light, which as of yet we don't have an understanding of what's generating them. These merging clusters also provide constraints on the matter-antimatter ratio in the universe. Thus, it's very important for astronomers to have the best possible understanding of what's going on in these merging systems. However, as many of you have reported, there's some mergers, such as Abell 520, which some refer to as the cosmic train wreck, and Abell 2744, that some refer to as Pandora's cluster, with their dark matter clumps and their ghost clumps, that provide serious challenges to our understanding of these systems and the physics involved. So the hope is that by studying systems, merging systems such as this at different stages in merging, astronomers can actually gain insight into the physics involved and realize the full potential of these interesting systems. I want to say that we are supported by some of you who pay taxes through NASA, and so thank you for that. I've posted these slides as well as the press release on the website link there, and it's also in the press release that you've been handed out. Thank you.
Thank you very much to all 4 of our speakers, Jack Hughes, Michele Trenti, William Dawson, and Larry David. Next, we will take questions. Again, please, if you ask questions, make sure to wait until the microphone has arrived at your place. And before you ask your questions, please state your name and affiliation. Same, of course, goes for anyone asking questions from the internet. Are there any questions in the room? Yes.
George Musser at Scientific American Magazine. This is for William Dawson. I have kind of 2 questions for you.
Sure.
Is this microphone working properly? Okay, it's
Yeah,
kind of weird from my perspective. First, you said the cross-section of the dark matter particle will be like a neutrino. So my question is, how does that compare to the other constraints on the dark matter properties?
Okay, so the constraint that we placed on dark matter is actually an order of magnitude looser than the current tightest constraint placed on dark matter particles. And this is through the self-interaction cross-section. This is the probability that a dark matter particle hits another dark matter particle. The current tightest constraint is actually from a work by Randall et al. And what they've done is they've used complex hydrodynamic computer simulations, so very powerful computer simulations, to simulate the bullet cluster. And then what they do, since they know what properties go into this simulation, it's easy for them to run different simulations and find which one actually matches the observations as much as possible. And so they're able to get a much tighter constraint than the simplified arguments that we do by just comparing and contrasting the scattering properties of dark matter with gas. So we hope to eventually run this cluster through these complex numerical simulations and improve the constraint and our understanding of them.
You said that there would be benefits to having a kind of a snapshot of a cluster at different stages of a merger. What specifically would those be, or have any already been gathered?
The hope is that there will be constraints. It's hard to improvements. It's hard to tell beforehand. But every time that we've studied things over time and the evolution of products, our understanding of the physics involved has always improved. It's just really, it's too hard to say right now whether or not the improvements will be significant. But the hope is there, and I think it's definitely something that we need to do in the future.
Okay, yep.
No.
Okay, this one's working. Martin Ratcliffe, freelance, and a planetarium guy too, also for Will. You notice on one of your PowerPoint slides you had this collision as the most energetic event in the universe.
So not
can you
this.
compare that to like gamma ray bursts and what order of magnitude we're talking about? I found that.
Okay, so I was speaking generally about merging clusters. Merging clusters are the most energetic events in the universe. But to answer your question specifically, these are about 10 to the 24 times more powerful than supernovae when stars explode. I'm sorry, but that was pretty much the closest thing in energy that I could come to these, and it's incomprehensibly, the gap between those energies is too large to even comprehend. So I apologize.
Okay, any other questions? Yep, there's another question.
Hi, Charles Choi, freelance. I just want to get two numbers from William Dawson and Michelle Trenti that just kind of whizzed by. Michelle, like you measured, was it 89, the velocities of 89 galaxies, was that?
No, we have no velocities measured. So
all right.
we have detected 5 galaxies, and because we expect only to see a much smaller number, we can conclude that 99.9% of confidence that we are seeing a protocluster in the Hubble image.
I'm sorry, I was misremembering. It was John. Was it 89 galaxies?
Yes, we measured 89 spectra with the VLT.
Right. And for William, you looked at the Musket Ball Cluster was what 6 to 7 billion years along its development, and the other cluster mergers that have been seen up to date have been, what was it? How many million or billion years?
Yeah, around 0.2 billion years. So we're really seeing it 2 to 5 times further progressed than other mergers to date.
Okay, great. I just want to make sure of the numbers. Thanks.
Okay, thank you. Any other questions in the room? Yes, there's a question up front.
For the large merging system, can you compare the redshift to the redshift of the bullet cluster?
Is this for El Gordo?
Yes.
Yes, so the redshift of the bullet cluster is, I think, 0.29, and our redshift is 0.87.
Look at it for the other cluster. I'm trying to put it all in redshift perspective.
Sure,
Sorry.
absolutely. I forgot to mention that. So the redshift of the Musket Ball Cluster is at 0.53, and that's 5 billion years ago, roughly.
Okay, this question was from Pamela Gay from Astrocast. Any other questions in the room? Any questions online?
No, we don't have any yet.
Okay, if there are no more questions, I would again like to thank our speakers. I would like to thank all of you for coming.
Wait, sorry.
Oh, got one?
See,
Okay.
I did ask, but
Okay.
Okay, just got one from Nancy Atkinson of Universe Today. She asks, how exciting was it to realize that you had found another bullet cluster? And I guess a second part of that question might be, how many of those kind of systems have we found so far?
Well,
So
Jack
I think
or I could.
Will and I should both answer that, because both of our clusters are sort of bullety-like. We actually put a lot of our observing time on El Gordo. We had a sample of clusters that we were studying, but we took a risk because we thought we had suspicions in some of our earlier data that there would be something interesting in the galaxy distribution. And so we actually did risk putting a lot of data on it. And we were very, very excited when we began to see the results, when the Chandra data came in. Our data came in very early, just about a year ago, and so we very quickly worked on that over a couple of months and came up with this idea of what was happening. So we were extremely excited about it and very motivated to get things published.
Yeah, we were thrilled too. It was actually a long process. So it began at AAS in Long Beach. I guess it was 3 years ago, where I happened to go to a talk by Dan Maroney, who works with the SZA collaboration, and found out that his survey overlapped our survey with the Deep Lens survey. And so we started comparing and contrasting what we found, and we found this particular system where the Sonia Zldovich measurement, which, as Jack explained, is a decrement in the cosmic microwave background, actually sat somewhat in between the galaxies and the mass that we had previously observed in the DLS. And so we were pretty excited about this, but I was gung-ho. I thought for sure we had found another merger, but Dan he's a much more respectable scientist, and he was much more cautious. And so we wrote a proposal for Chandra with the help of Jack. And I remember it was last year, I think, I was sitting side by side with Jack as we were processing the Chandra X-ray image, and then we processed that, and then we overlaid it on the galaxies, and it was pretty clear. Oh, and by that time we had also had a much better resolution weak lensing mass map, and so we overlaid it on both of those. And yeah, I remember being particularly thrilled. To answer the question about how many these are, so mergers have been found in different states. So for example, the Coma cluster is a merging cluster right now. It's not like these dissociative merging clusters where you actually see the gas dissociated from the dark matter in the galaxies. So these where, like I was saying, the dissociative ones where they're spread out, these dissections of the cosmos, these are particularly rare, and less than, I would say, 10 of them have been observed to date. Now, because of the interest piqued by the bullet cluster, a lot more people are looking. We're getting a lot more time with Chandra, and we're starting to actually find more of these.
Okay.
Quick related question. Do you have other forms of ammunition you can use for names in the future? Maybe you can get funding from the NRA.
Oh, brilliant.
Now that's
You can be
thinking
a
outside the
co-author on
box.
our next paper.
Okay. Any other questions in the room or online? Okay, I would like to thank our speakers again, thank the audience. Our next press conference is right here at 12:45 p.m. this afternoon on the universe at very high energies. We'll be talking about everyone's favorite, black holes, as well as sources above 10 giga-electron volts in the Fermi sky, and an unveiling of the hard X-ray universe. So please come back. Thank you.